While humanity was distracted by terrestrial winter solstices, a 500-pound titanium and carbon automaton was quietly executing the most violent and mathematically complex orbital maneuver in the history of spaceflight. On the 24th of December, 2024, while the majority of our species was engaged in terrestrial winter traditions, a solitary, metallic emissary achieved a milestone that classical astrophysics once deemed mechanically impossible. A specialized spacecraft, possessing the approximate mass and dimensions of a standard terrestrial automobile, penetrated the outer atmospheric boundary of our local star. It did not merely observe the Sun from a proximity previously thought unattainable, it physically entered its atmosphere. At the moment of this historic perihelion, the probe was traveling at an astonishing velocity of 430,000 miles per hour. To contextualize this kinetic energy, an object moving at such a speed within Earth's atmosphere would traverse the distance between New York and Los Angeles in roughly 20 seconds. As it plunged into the stellar abyss, the intense electromagnetic interference severed all communication with our planet. The engineers and astrophysicists stationed at Mission Control were left in total silence, relying entirely on the precision of their mathematical models to dictate whether their creation would survive or be instantly vaporized. This is the empirical account of how human engineering successfully touched a star, and the paradigm-shifting data we extracted from the inferno. When analyzing the dangers of solar proximity, the layperson intuitively points to the Sun's surface temperature. The photosphere burns at a relatively predictable 10,000 degrees Fahrenheit. While this thermal output is catastrophic to organic matter, it is a known, manageable variable in the realm of advanced materials science. The true thermodynamic anomaly, and the primary existential threat to any solar probe, is the corona. The corona represents the Sun's outermost atmosphere, a turbulent, invisible envelope of ionized gas or plasma, projecting millions of miles into the vacuum of space. The data regarding the corona presents a profound paradox that seems to violate the fundamental laws of thermodynamics. While the solar surface registers at 10,000 degrees, the temperature within the corona exponentially spikes to an incomprehensible 1 to 3 million degrees Fahrenheit. Consider the physical impossibility of this under standard thermal distribution models. If you distance yourself from a localized heat source, such as a combustion reaction, the ambient temperature decreases, yet the Sun exhibits the precise inverse of this behavior. As you move further away from the nuclear fusion reactor at its core, the atmosphere becomes up to 300 times hotter. Within the scientific community, this is formally classified as the coronal heating problem. For over 8 decades, it has stood as one of the most glaring deficiencies in our understanding of stellar mechanics. However, resolving this anomaly is not merely a pursuit of academic vanity. The corona is the birthplace of the solar wind, a ceaseless, violent torrent of charged particles radiating outward at velocities between 200 and 500 miles per second. This plasma stream continually bombards Earth's magnetosphere. When these energetic particles collide with our magnetic shield with sufficient force, they induce severe geomagnetic storms. These electromagnetic disturbances possess the capability to degrade satellite orbits, blind GPS navigation systems, sever high-frequency radio communications, and induce catastrophic, cascading failures within global power grids. Therefore, mapping the mechanics of the Sun is a critical imperative for the preservation of modern, electricity-dependent civilization. Before we deconstruct the telemetry of the mission itself, we must examine the historical context of its namesake, an anomaly, in its own right, within NASA's operational protocols. In 1958, an astrophysicist named Eugene Parker theorized that the Sun was not static, but rather a dynamic entity constantly exhaling a supersonic stream of charged particles across the solar system. He coined the term solar wind. When Parker submitted his mathematical models to the preeminent physics journal of the era, the peer review process rejected it. The established scientific consensus argued that space was a perfect vacuum, and Parker's calculations contradicted accepted physical laws. However, Parker vehemently appealed the decision. The manuscript was ultimately published only due to the authoritative intervention of the journal's editor, Subramanian Chandrasekhar, a physicist who would later be awarded the Nobel Prize. Within 2 years of publication, early satellite telemetry vindicated Parker entirely. The solar wind was not a mathematical fiction. It was an empirical reality. In recognition of this monumental contribution to heliophysics, NASA broke its own precedent. For the first time in the agency's history, they named a spacecraft after a living researcher. Eugene Parker, at 91 years of age, observed the launch of his namesake in 2018. He lived until 2022, witnessing the initial data streams that would revolutionize his life's work. Let us transition to the mechanical hurdles of the mission. The engineering problem that plagued aerospace designers was formidable. How does one construct a functional sensor array capable of operating within a stellar atmosphere? During its closest orbital passes, the sun-facing surface of the Parker Solar Probe is subjected to temperatures exceeding 2,500 degrees Fahrenheit. This thermal load is sufficient to liquefy steel, aluminum, and titanium. Yet the delicate scientific instrumentation housed directly behind the primary heat shield operates at a stable 85 degrees Fahrenheit, a standard terrestrial room temperature. This thermal isolation is achieved across a barrier measuring a mere 4.5 inches in thickness. The solution lies in a masterpiece of modern materials, science known as the thermal protection system. This shield is constructed from 2 panels of superheated carbon-carbon composite, which encapsulate a core of specialized carbon foam. This foam is structurally composed of 97% empty space. It is exceptionally low in mass, yet maintains high structural integrity, serving as one of the most efficient thermal insulators ever deployed in a vacuum. Furthermore, the sun-facing exterior is treated with a proprietary white ceramic coating designed to maximize the reflection of solar irradiance. But this brings us to the most frequent point of confusion among observers. If the corona is 1,000,000 degrees, why does the spacecraft not instantly sublimate into gas? The answer requires a strict differentiation between 2 physical concepts: temperature and heat. Temperature is a measurement of the average kinetic energy, or speed, of individual particles. Heat, conversely, is the total amount of thermal energy transferred when those particles collide with mass. The solar corona possesses an incredibly high temperature, but it is simultaneously a near-perfect vacuum. The particle density per cubic centimeter is infinitesimally low. Therefore, while the few particles that do exist are vibrating with immense kinetic energy, there simply are not enough of them colliding with the spacecraft to transfer a lethal amount of heat. To utilize an analogy, placing your hand in a hot oven will not immediately burn you because the air is not dense, but touching the dense metal rack inside the oven will cause instantaneous tissue damage. The Parker Solar Probe survives because navigating a 1,000,000-degree vacuum is a manageable thermal load for a precisely engineered carbon matrix. Beyond thermodynamics, there is a secondary mechanical challenge: kinetic stress. Traveling at 430,000 miles per hour, the thermal expansion and contraction forces threatening to shear the probe apart are immense. To counteract this, aerospace engineers integrated flexible, articulated joints throughout the chassis. The spacecraft is intentionally designed to deform and flex in response to structural stress, rather than maintaining a rigid posture that would inevitably result in catastrophic fracturing. Navigating to the sun is equally complex from a mathematical perspective. Launching a projectile directly into a star from Earth is impossible using current propulsion technology due to orbital mechanics. Earth travels around the sun at approximately 67,000 miles per hour. Any probe launched from our planet retains that immense lateral angular momentum. If you aim directly at the sun, the probe will simply enter a highly elliptical orbit and continuously miss its target. To shed this orbital velocity, NASA utilized a complex series of gravity assists. By plotting a trajectory toward Venus, the mission team used the planet's gravitational well to decelerate the probe. Over a period of 6 years, the Parker Solar Probe executed 7 distinct Venus flybys. Each encounter bled off lateral velocity, tightening the probe's orbit and allowing it to fall progressively closer to the solar surface. Throughout these descending orbits, the instrument suites were continuously recording data, fundamentally altering our understanding of solar dynamics. The telemetry revealed that the solar wind does not project outward in a uniform, linear fashion. It is highly turbulent. The magnetometers detected sudden, violent reversals in the local magnetic field. These anomalies, categorized as switchbacks, occur when the magnetic field lines fold back on themselves in a zigzag pattern. They appear in staggering quantities and are now believed to be the primary mechanism responsible for accelerating the solar wind to its terminal velocity. Furthermore, the probe successfully navigated directly through coronal mass ejections, the massive expulsions of magnetized plasma, recording their internal structure from the inside for the first time in human history. This rigorous data collection culminated on the morning of December 24, 2024. At the Johns Hopkins Applied Physics Laboratory, scientists monitored the telemetry as the probe approached its minimum orbital intersection distance. As predicted by the mission parameters, the spacecraft entered a zone of total communications blackout. The sheer volume of electromagnetic radiation emitted by the corona at that proximity jammed all radio frequencies. The probe was entirely autonomous, millions of miles from Earth, flying at record velocities through an alien atmosphere. For context regarding this proximity, the planet Mercury never approaches closer than 28 million miles to the Sun. The Parker Solar Probe was operating at a distance of merely 3.8 million miles. For 2 days, the scientific community waited. Finally, on December 26th, the Deep Space Network captured a faint, localized radio beacon. It was a pre-programmed carrier tone, a binary confirmation of survival. The engineering parameters held. The instruments were functional. When the high-gain antenna finally transmitted the stored data packets to Earth in early 2025, the results were unprecedented. The Wide Field Imager for Solar Probe, or WISPR camera, had captured high-definition visual data of the solar wind at its exact point of genesis. The imagery showed plasma streams detaching from the coronal structure and accelerating outward. It was the astrophysical equivalent of finally locating the subterranean source of a massive river, after decades of only observing its delta. The datasets also provided empirical evidence for a theoretical model known as the solar wind U-turn. During a coronal mass ejection, not all plasma escapes the star's gravity well. The probe's sensors recorded vast quantities of magnetized material being captured by the Sun's magnetic field lines and violently pulled back into the corona. This feedback loop alters the magnetic topology of the Sun and directly influences the volatility of subsequent plasma ejections. Understanding this mechanism is the missing variable required to accurately predict the severity of future solar storms. Furthermore, regarding the coronal heating mystery, the initial data strongly correlates the presence of the aforementioned magnetic switchbacks with the extreme temperature spikes. It appears the corona is heated through a highly complex, turbulent interaction of magnetic wave activity and sudden magnetic reconnection events, where field lines break and snap together, releasing massive amounts of kinetic energy. The Parker Solar Probe continues to execute its perihelion passes, gathering data during the current solar maximum, a period of peak volatility in the Sun's 11-year cycle. The practical implications of this mission cannot be overstated. Currently, our terrestrial early warning systems for space weather provide a maximum of a few hours of notice before a solar storm impacts our magnetosphere. This is an insufficient window to safely power down global electrical grids. A direct impact from a massive coronal mass ejection, similar to the Carrington event of 1859, would induce geomagnetic currents that could physically melt transformers across multiple continents. The resulting power grid collapse would take years to repair, plunging heavily populated regions into extended blackouts and causing unimaginable economic and societal disruption. The empirical data harvested by the Parker Solar Probe is the foundational blueprint required to construct advanced, predictive heliophysics models. By understanding the precise mechanics of how solar weather is generated at the source, we can transition our early warning capabilities from a matter of hours to a matter of days. This advance notice is the critical buffer needed to safeguard the trillions of dollars of electrical infrastructure that underpins the entirety of modern human civilization. NASA did not merely touch a star to satisfy scientific curiosity. They executed this mission to secure the technological future of our species. If you value this level of rigorous scientific analysis, engaging with the algorithm by liking this content ensures its distribution to a wider, analytically minded audience. And I highly recommend subscribing to this channel, as our next analysis will decode the anomalous telemetry recently transmitted by the James Webb Space Telescope regarding the edge of the observable universe, data that directly contradicts our current standard model of cosmology.